Hello, everyone. So this is not such a technical talk. It's more like a talk about application, actually, and it's mostly work of my PhD student Luna, who is not here today. But I think it's very interesting to actually see the limits of Stan when it comes to really complex hierarchical kind of models. In this case, it's kind of what we call structural equation models. And when we think about latent variables in psychology, we think about intelligence, creativity, personality traits. And I came from psychology and I've moved away since. But it's still interesting to me to think about latent variables because there's such a strong connection because the theory and how we define and measure them, and also how we then actually estimate them with statistics, because kind of without proper statistical models to estimate and then do something with them, we wouldn't even have like proper latent variables. So the statistics plays a core role even in psychological theory. And there's two parts. Let's see if I have enough time for both. And here I'm going to talk first about distributional structure and equation models. I'm essentially asking what aspects of a latent variable may vary. So usually, let's say we have intelligence and creativity, we can ask, are more intelligent people more creative? Just dropping how exactly we measure intelligence and creativity. Once we have these latent variables, we could just ask a kind of average intelligence predicts average creativity. Anyway, but of course, this has been already done, so it's a bit boring, so we are making it a bit more complicated by essentially asking which aspects, in this case, which distributional aspects of latent variables may vary or may be predicted by other latent variables. And in this first paper by Luna and me, we did so in the Gaussian case because this is already messed up enough. I wanted to do everything at once and then it didn't work, so we just focused on the Gaussian case. Let's start. And I have an actual motivational example here. It's from a paper by Mada et al. And shout out to Ruben Aslan, who's the second author here, who gave us access to the data. So we could actually try it out. They were analyzing, or they were predicting negative effect with neuroticism. So neuroticism is a major personality trait that describes a person's tendency to feel negative emotions such as anxiety, worry, sadness, etc. And negative effect would just describe a person's current negative emotional state in a given moment, not like a general purpose dimension that is more or less stable over time. The idea also, the way we essentially ask questions about neuroticism, the way we measure it, it's plausible to assume that it may not only predict the average negative effect, but also its variability. And that's kind of a distributional question in a way, because we are having one latent variable, neuroticism, and it predicts different aspects of another latent variable, negative effect, in this case the average, the mean negative effect, and its variability. And what they did in the paper, and what other papers so far did, they were always having like some kind of two-step procedures in a way. They're estimating the latent variable somewhere, then as kind of parameters in our model, then they're taking the posterior means, for example, and then they're using the posterior means as predictors in a way, which of course kind of breaks all the uncertainty propagation. But if we want to do everything in one model, just like estimating these latent variables and then letting one predict the other, we really have to use space, especially in these distributional manners, because there's no way that optimization algorithms without priors will work. The maximum likelihood estimates will not exist. Even with priors, kind of optimization kind of breaks down. So we really need sampling, we really need informative priors to somehow make this work. So to give you a sense of, if you're familiar with these kind of notation, do I have a pointer? Don't think so. Anyway, so we see on the top the zeta one is our latent variable. Let's say it's kind of neuroticism, and it's predicted by, or like it's measured by 5 items, y11 or y1 to y5, and usually we just like leave it like this, but now that we actually notice that a latent variable can have different distributional parameters that we may seek to predict, I'm having like smaller circles inside of the zeta 1 to say that zeta 1 has a mu, which we could potentially predict, and a sigma, like a standard deviation, which we could potentially predict if we assume our latent variable to be normally distributed. And so we would say zeta 1 is normally distributed, and for identification purposes we are fixing the mean here to 0, and then the individual like observed responses, let's say the questions in a personality trait questionnaire Y are then basically like a linear regression, so to speak, of our latent variable, with lambda being the factor loadings that define how closely the question I'm asking is related to my personality trait. And we can actually fit these models in BRMS by hacking it in a way. BRMS has a missing value imputation notation, so if you have a variable that has a bunch of missing values and a bunch of observed values, you can use these AI terms. So if you put mi on the left-hand side of the tilde after this pipe, then it means this variable is going to be allowed to have missing values. And then when you want to have this variable which is allowed to have missing values and use it as predictor somewhere else, and you put it on the right-hand side and wrap it in AI. Yeah? So on the left-hand side, it's basically saying this variable is latent. On the right-hand side, this is a predictor, which is a missing value variable. So now, latent variables are nothing else than a variable with only missing values. Yeah? So we can kind of hack latent variables into BRMS through pretending this is kind of just a bunch of missing values, while actually it's all missing values. This has some drawbacks, and I've promised for years to people that I will actually implement a better parameterized version of latent variables, and I haven't done it. So if somebody has the motivation at the time, I would appreciate it. Okay, so now to the interesting part. After we have defined the individual measurement models for our latent variables, we now can go ahead and use zeta 1 to predict not only the mean of another latent variable zeta 2, but we can also predict its standard deviation. Yeah? So that's why we have this edited notation where we are like actually having two errors from zeta 1 to zeta 2, predicting both mu and sigma. And also there's some identification going on, but essentially the way this would look in BRMS, if we exclude the measurement models here for now, of course, we would have zeta 1, which is a latent variable, with zeta 2, which is a latent variable, but zeta 2, both its mean and its standard deviation are going to be predicted by zeta 1. Yeah? And then there's like a bunch of intercepts which you need to fix, etc. There's this is half pseudocode because I left out a lot of identification constraints, but if you're really interested, you can check out the paper. But there are some complications involved in this. And of course, this is like a very simple model, but we can make this arbitrarily more complex. For example, psychologists love mediation in a way that, zeta 1 affects zeta 3, and then zeta 3 affects zeta 4, and the same with zeta 2 paths. So there are lots of paths that could go from both mean or standard deviation, or any kind of distributional parameter of our latent variables. And you can imagine this gets complicated really fast because we have, in Stan or anywhere else, we have so many parameters, because each value of the latent variable is a parameter. So for each person, we have one or more parameters, so this scales very quickly with data size. And we have highly complicated relations between lots of these parameters, so sampling isn't too easy. So this, for example, mediation, or we could even go for something like an interaction model, where we basically multiply latent variables with each other to then form like a predictor term, which is kind of trivial in Stan because we have these two latent variables. Even though they're parameters, we can multiply them, no problem. But if we were to do this in a standard structural equation modeling framework, it's just, people have been working on hacks for decades, and none of this is really satisfactory. Well, in Bayes, it's just multiplication. Anyway, and to the results, even though these models were really complicated, we actually managed quite well to fit them in Stan, which is surprising to me. So this is one way I kind of moved on also to other research topics, because Stan was working too well and I got bored. So we see on the top, we see the calibration. We see most of the parameters are like all of the parameters, including the log likelihood, which is kind of a really good check for model calibration. They are well calibrated. On the bottom right, we see we have good parameter recovery, both in terms of bias and mean RMSE. However, we do see also when we check the convergence, on the very right, the black stripes, these are model runs on simulated data that did not converge well, even after we did serious efforts to make them work. So here we have actually found a model class that even though we are trying really hard, we have informative price, we're optimizing parameterization, etc., still sometimes we are running into convergence issues. And perhaps that's going to be improved with better initialization or mass matrix adaptation, etc. I hope. And I think this is actually interesting insofar as I've rarely come across a model class in Stan that gives me this amount of trouble. And the results we do see here are actually, it's not really cheating because we say what we do, but we are excluding all the badly converged ones, so all where the r-haters were greater than 1.05, we're excluding from the calibration, etc. Which is kind of like truncation. If you feel in SBC, you can kind of truncate your prior based on, you can truncate your simulations based on data-dependent quantities, in this case the convergence. And SBC remains valid, but we are changing implicitly the prior, so perhaps these were just bad parameter simulations. I'm not sure. But we also do see these issues in real data. So we have the interaction model, and also there things work out pretty well. We have still some convergence issues, which I hope to be able to resolve at some point. Okay, part two. So in the first part, we have thought about distributional modeling of the latent variables. But now we can also do it in a different way and ask essentially, how can we define a latent variable? So what is a latent variable again, in a way that usually in structural equation modeling or like all the psychological modeling with latent variables, we are defining latent variables based on the means of their observed indicator variables, like questions in a survey. But what if we define latent variables not only based on the means, but also on other distributional aspects of the observed variables? And that's what we did in the other paper. And as a motivational example, conveniently enough, we can use the exact same paper and ask kind of the reverse question. So previously we predicted negative effect with neuroticism, but now we can also predict neuroticism with negative effect the other way around. And can ask not only the mean of the negative effect, but also its variability may predict neuroticism. Yeah, so essentially the previous example in reverse. And now we can go ahead and say, okay, I have a bunch of observed variables, of manifest indicators. We say, in this case 3, I used to have 5 in the previous picture, but 5 was too much for the slide, so I just used 3. But now we are not only defining a single latent variable based on these 3 observed variables, but 2. So one of the latent variables is identified or defined by the means of these observed variables, and the other one is observed by the standard deviation. So our distributional aspect is now on the level of the observed variables, not on the level of the latent variables. Of course, we could combine them if we were really crazy. And I just used an example here, again, with a normal distribution, but of course this scales for other kind of distributions, and we in fact also tried out different ones. In BRMS formula syntax, again abusing MI, this would look as follows. So we would define 2 latent variables, zeta mu and zeta sigma, and then our individual observed variables yi from y1 to y3 would basically, zeta mu would basically learn from the mean of yi, and sigma mu, it should have been zeta sigma, I will correct this, is going to be informed by the standard deviations of our observed variables. And then, this is just the measurement part, and then we can go ahead and use these so-defined multiple latent variables to predict other stuff. And I was very creative, so I just called this other one zeta other. In this case, it's kind of, let's say, neuroticism, for example. Yeah, so we are taking this, we're having zeta other, and we're seeking to predict it both by this latent variable identified by the means and by the latent variable identified by the standard deviations. In this case, should have been zeta sigma, not sigma mu. I messed up the notation. And then now the natural question is, this part of the model and this part of the model, are we doing this in one model, like in one STEM model, or are we doing this in 2? And previous approaches, without thinking of it like that, they've been doing different, kind of a 2-step approach. We first estimate these latent variables in some way or form, then we are taking the, let's say, posterior means, and we are using them as predictors in the second stage model, which kind of, again, drops all the uncertainty propagation. So I would say we want to have all of this in one model. And in BRMS and STEM, we can do so. And of course, we were hoping for to see benefits in, I don't know, recovery of the true parameters in simulations and uncertainty calibration, etc. And we did see them, but we're actually like having to search for a little bit. So I realized in terms of visualization after hearing Matthew's talk, this is like a really bad slide for this, but I made it. I copied it like yesterday, and I just didn't have the time to fix it. So let's focus on the left-hand sides of the plots. I really would love to have a pointer right now. And we have 4 methods which we are comparing. What we call Oracle is kind of using the true latent variable values which we have access to in simulations. So this is the best we can possibly do. Then this DFLVM is kind of our approach, where we have this one-stage distributional measurement models. And then we have multiple 2-stage approaches which have, basically fit 2 different models after each other without proper uncertainty propagation in between them. And this is now when our 2nd stage model is actually Gaussian identity, so it's like just a linear model. And what we do see here there, without you actually having to look at all the plots in detail, is that we don't need to go through the effort of fitting everything in one model if we use the right kind of 2-stage approach, which in this case is this 2-stage LC model here. It actually works well in almost all the cases. Which is actually interesting, because we are not propagating a lot of uncertainty, and somehow we're still getting most of the time good estimates. So bias is almost 0, RMSE is low, and log gamma is a test statistic for calibration. So as long as we are kind of on that line, the dashed line or upstairs, then we are like well enough calibrated. So this was a bit disheartening at the start, because we're going through all the effort. It costs so much time to fit stuff, instead it doesn't even help. And we analyzed this a bit, and it turns out there's like at least 3 different factors contributing to whether this uncertainty propagation is needed, and different kind of factors that affect bias of these models in different ways. And in linear models, they're exactly offsetting each other in certain ways or forms. So what we did is we changed the 2nd stage model of zeta other, essentially, let's say, to a Poisson regression, with a log link. So specifically important is here the nonlinearity, and suddenly, for example, if we look at the bottom left plot, especially for the tau 2 equal to 1, where we have a lot of variation between the latent variable values, suddenly we see very bad calibration for both 2-stage approaches. So we find that indeed having like everything in one model, proper uncertain propagation does help, but we would need to have some nonlinearities in the model to find them reliable. All right. So to summarize, I know this is kind of StanCon, but all of this is done in Stan, and and without Stan it really would be impossible. So these kind of models have a lot of potential for psychological research, I believe, if people actually are, can easy enough apply them through BRMS and Stan. And Stan BRMS do a good but imperfect job at estimating these posteriors. And I believe that like improvements to Stan's kind of warm-up and general sampling may improve this in the future. There's also other things that I didn't talk about so much, which is that simulating realistic data from these models is really complicated. Because as soon as our priors are big too wide, then our simulated data completely explodes. So the question is if our convergence issues are actually due to trouble with the sampler on realistic data, or just because we had produced so much garbage data in our simulation. So whenever we run SBC or kind of simulation studies, it's almost as hard to fit the model than it is to just simulate realistic data. So there's a bunch of other stuff about model parameterization and identifiability that I hope to make more efficient in the future, that will improve fitting these models. Thanks.
Thanks a lot. We have time for one question. Over there, I think. Thank you. Good catch.
Thank you. Oh my God, sorry. Thank you for the talk. A question about how do you think this relates to topics in survey statistics? Like there, oftentimes you have some sampling process, and you also basically have latent things that you're trying to measure in your survey, and then there's this work, for example, I think Gelman and Little, they have some papers on like the advantage of including also the sampling process in your model?
Yeah, I'm almost sure. It's like it's often done, for example, server research. The kind of models, just more like historically, are done a bit differently. It also depends on the amount of data you have, because these kind of full latent variable models, they scale not so well with huge amounts of data. But I believe so, and we have kind of, in an indirect manner, we have been also doing this, although we have been doing two-step procedures to make it computationally feasible. So I believe that people are using latent variables also there. It's just a different tradition.
Mm-hmm. Thank you.
Thanks.
Thanks a lot.